Okay, welcome back everyone to the online Graphs and Matroids seminar. Today we're happy to have Jim Geelen talking about average plane size. So whenever you're ready, Jim.
Okay, thanks, Zach. Yeah, so I'm going to talk about a project I've been working on with Rutger Campbell and Matthew Croker over the summer, maybe even a bit longer than that. And it's a result that I'm really excited about because I could pretty much explain it to anyone in the street. And in fact, I have explained this to people at my climbing gym. They may have been massively underwhelmed, but I think they understood what the results said. So failing the fact that that didn't actually land as being an interesting fact for them, you can explain it to anybody. So let me start off by telling you a precursor result due to Melchior from 1941. So Melchior's result is that if you take a simple rank 3 real representable matroid, the average line length is always going to be less than 3. So for example, here I've drawn the cycle matroid of K4. We have 4 lines of length 3 and 3 lines of length 2. So of course the average line length is going to be a bit less than 3. It's 18/7 if you compute it. And Melchior's result says that's going to be the case for whatever real representable matroid you take. Now, while Melchior's result is stated for rank 3 matroids, it of course applies to matroids of rank at least 3 because you can truncate from high rank down to rank 3, keeping the same set of lines. And when you truncate, you preserve real representability. It's just projection. So, and the same thing will hold for the other results that I talk about later. When I talk about a specific rank, you should think about that also applies in higher rank. Now, while it's not particularly important for this talk, I'm going to explain how Melchior proved his result because it's a really, really pretty proof. But we'll see later another proof of Melchior's result, or a weaker version of Melchior's result, that uses the sort of techniques that we generalize. Okay, so the proof of Melchior's result goes via a sequence of rewordings of the result. So first of all, let me just state it as a result in projective geometry instead of using matroid theoretic language. So I started off with a rank 3 matroid. So that's, you can think of as just a set of points in the real projective plane, not all on a line. And then I'm going to look at lines that are spanned by 2 of these points. Any 2 of these points, I look at the line and I count up the number of the points that are on the line. And the average is less than 3. Right? So that's just a restatement of the result in terms of points in a projective geometry. Sorry, points into projective plane. I could also, didn't have to go to the projective plane. This could have just been the real plane. But the advantage of talking about the projective plane is you can use the point line duality in the projective plane and you can restate it this way. So I turn my points into lines and my lines into points. So for example, those 6 points become 6 lines in the projective plane. And the condition that says that they're not all on a single line, the 6 yellow points are not all on a single line, translates to the lines don't all go through one point. And now, instead of looking at the spanned lines, what I'm going to do is I'm going to look at the intersection of 2 lines. So I get a bunch of points that are the intersection of 2 of these lines. The red points there are the intersection of 2 lines, and the blue points are intersection of 3 lines. So they're all intersection points, and some of them I have multiplicity 2, and some of them have multiplicity 3. And they correspond, so the 3 red points there correspond to the 3 2-point lines in my diagram on the left. And the 4 blue points correspond to my 4 3-point lines in the diagram on the left. So in this formulation, you're trying to prove that the average multiplicity of an intersection point is less than 3. And this was Melchior's, this was the setting that Melchior used. He was talking about lines in the projective plane. When you're in the projective plane, you can basically project onto the circle. So you can project from the projective plane onto the circle, and your lines turn into great circles. Sorry, you can go from the projective plane onto the sphere, and then the lines turn into great circles on the sphere. And your points turn into pairs of antipodal points on the sphere. And so now I've got a collection of great circles, not all meeting at a common point. Of course, if they meet at one point, they meet at 2 points, because all pairs of great circles meet twice. So basically, I'm saying I've got a collection of great circles, and they're not all just lines of longitude. And now I look at the average multiplicity of an intersection point, that should be less than 3. So in this picture here, I've got the yellow intersection points being things with multiplicity 2, the blue ones being points with multiplicity 3, and the purple ones being intersection points with multiplicity 5. And the average, if you go average over all of these points, you'll get less than 3. The nice thing about this version is as soon as you've got a bunch of great circles and their intersection points, you have a planar graph. And the average degree in a planar graph is less than 6. And the degree of a vertex is twice its multiplicity. So the intersection points of multiplicity 2 correspond to degree 4 vertices, etc. So there's the theorem. That's Melchior's result. The average degree is less than 6, and so the average multiplicity of an intersection point is less than 3. If I knew this the last time I taught introductory graph theory, I think I probably would have given this as an application to Euler's formula. Okay. So that's just a proof of Melchior's result. Now we want to think about an analogous result for plane size. So instead of thinking about points in the plane, we now think about finite set of points in 3-dimensional space, or in other words, I've got a simple rank 4 matroid, and I want to know, is it true that if I think of a simple rank 4 matroid, am I going to get an absolute bound on the average plane size? The answer is no, because it could be that all of my points lie on 2 lines. Planes all have at least 3 points, so they're going to have 2 points on one of those lines, and that means you actually contain one of the lines. So I can make those lines arbitrarily long by adding points, and I can make the average plane size arbitrarily large. So it's not the case that your average plane size is bounded. But the beautiful thing is that this is essentially the only problem. So our main theorem says that the average plane size is bounded by an absolute constant unless your matroid is the direct sum of 2 lines. Okay, so I could take any simple rank 4 real representable matroid that's not the direct sum of 2 lines, then there is some absolute bound on the average plane size. So that's pretty much like Melchior's result. I can imagine that you are probably wondering about the constant. I don't know the constant, but this is not like constants in some of my other theorems that are very, very silly. This is, I would imagine, would be something like 3-digit, 4-digit, 3 or 4-digit constant. I mean, like, it's not a horrible bound. It's like if you go through the proof, it's probably going to be like 1,000 or something like that. The reason we don't know it is because our result relies on some other results where they don't state their constant. So one would have to go back through all of these proofs and actually compute the constants in all of these proofs. But none of the proofs are using weird constants. It's just they don't state them explicitly. It would just be a matter of work to go through all of those proofs and turn them into an explicit number. Whatever we get, it's going to be far from the truth. So I think probably the right answers actually are like, it's probably 4. And this is just based on a sheer guess, based on the fact that Melchior in rank 3, lines in rank 3 give you 3, planes in rank 4, I think are going to give you 4. I can't construct counterexamples, so that's basically what we think might be true. Okay, so now I want to go through a sketch of a proof of this theorem. So let me quickly fix just a bit of notation before we do that. So M is always going to be some simple n-element real representable matroid with rank at least 3. L will be script L will be the set of lines, and script P will be the set of planes. So the first thing I want to do is I want to go back and reprove Melchior's theorem using the kind of machinery that we use for planes. This machinery is a lot less precise than in the first proof of Melchior's theorem I gave you. So I'm not going to prove the same bound. I'm not going to give you less than 3. I'll show you a bound for some explicit constant that we'll state in a bit. But at the moment, you just think along the lines, I'm trying to get some fixed constant bound on the average line length. So I have a rank 3 real representable matroid, and I'm trying to get some constant bound on the average line length. And we're going to compute the average in the sort of the usual way. I'm just going to take the sum of the line lengths divided by the number of lines. And if you think about that, what you realize pretty quickly is that you need a very good estimate for the number of lines if you want this to work. I want to get a constant bound on the average line length. So I need my estimate on the number of lines to be correct within a multiplicative factor. If it's not always correct within a multiplicative factor, I'm not going to be able to prove a constant bound on the average line length. So that's what I want. And fortunately, geometers have thought about this. And there are results that give you good estimates on the number of lines in a rank 3 real representable matroid. And it turns out that the longest line length plays an important role in these bounds. So there's an old theorem due to Beck that says that either your longest line contains nearly all the points, or the number of lines is in the order of n squared. The specific numbers in this result come from a paper of Desiu, but if you don't look at the 0.9 and the 1/12, that was a theorem of Beck's. He found weaker bounds than this, so we're going to use Desiu's bounds. So in our case, so either the longest line contains 90% of the points, or the number of lines is 1/12 n squared, where n is the number of points. Now, if the number of lines is at least a 12th n squared, then you actually have you have what you're looking for, because the number of lines can be at most n choose 2, which is in the order of n squared. Every pair of points defines a line. So if your number of line is in the order of n squared, we've got a good estimate on the number of lines, something that's correct within a constant multiple. So you only have to worry about the case that your longest line is very long. But if D2 contains 90% of the points, when you take a yellow point off the line and you look at all the lines through it, right? So you fix one of these points off the line and you look at all the lines through it, not many of those lines that go through a blue point can contain another yellow point. So most of the lines are going to be 2-point lines. And you're going to get basically the number of yellow points times the number of blue points, like in that order of lines. So using that reasoning, it's an easy application of Beck's theorem to get that the right estimate that you're looking for is n times n minus the length of the longest line. So that's a good estimate on the number of lines. Okay. So we have the formula for the average. We now have this good lower bound on the number of lines. And to prove our result, what we need to prove is that the sum of the line lengths is bounded above by some constant times n minus the length of the longest line. Okay. When I see that right-hand side, that makes me think of taking all pairs, where I take one element arbitrarily, and then I take a second element off of the longest line. Right, that's kind of a natural thing to do. And I want these pairs to span lines, so I want E not to be F. But certainly the number of these pairs is bounded above by 12 times the number of lines now. I've got that. And now I need to relate this value, this set script T, I need to relate that to the sum of the line lengths. So now I need to look at the lines in, I need to look at lines in L and ask how many pairs in script T do they define? Well, the long line doesn't contribute any, right? The long line is exceptional. I can't choose a point. I can't choose the choice for F because it's in, like, all my points in my longest line are in the longest line. So I can't choose an element for F. So the longest line is exceptional. But for the other lines, let's take any other line in my collection and let's count how many different pairs I get. I claim that I get at least the size of the line minus 1 squared distinct pairs. And the reason that's true is you choose the second element first. So you choose the point off the longest line. And there's the size of L minus 1 choices for F. And now when I choose E, the only restriction for E is that it's not F. And so I get the size of L minus 1 squared distinct pairs. So every line contributes at least L minus 1 squared distinct pairs to this set script T. And of course, every pair of points determines a unique line. So if I take different lines, they're going to be determining different pairs. And now I just need this inequality here, which is just simple algebra that the size of L minus 1 squared is at least 12 times the size of L minus 4. So now what I'm going to do is I'm going to sum up over all of the lines except for the longest line, the size of L minus 4. And that's going to give me, based on this observation up here, at most a 12th the number of pairs that we got. The total number of pairs, these special pairs. And the number of special pairs is at most 12 times the number of lines. And so the sum of the line lengths minus 4 is less than or equal to the number of lines. And that tells you that the average length of one of those lines is at most 4. Okay. Right, I got the average of these numbers is less than the number of lines. So now if you just divide through, it says the average of L minus 4 is less than or equal to 1. Have I lost a plus 1 here? I think I have lost a plus 1 here. Maybe it's 5. That should be 5. The average length of one of these lines is at most 5. And so now I only have to look at the longest line But the number of lines is more than the size of the longest line, because you can just fix a point outside. And so the longest line is going to contribute at most 1 to the average. And so you get a bound on the average line length. Well, it says 5 there, but I think actually it's 6. Okay. Is that clear? They don't want me to clarify anything there, because I mean, we're going to go through when I go through planes, I'm going to do it more quickly. So if there's anything you want me to go over that, this would be a good time. Nope.
Yeah. What's your conjecture about that constant in the plane?
In the plane, it's 4.
Okay. So what about K5? K5's above 4.
Is it?
Yep.
The average plane size in K5?
Yep. 70 over 15.
What?
14
well,
over 3.
Well, then I'm wrong.
Okay.
What is it?
I think it's 15 over 3.
The planes.
14 over 3. So there are 5 6-point planes come from deleting a vertex. And there are 10 4-point planes. You come by just picking an edge.
What do you mean by picking the edge? Oh, you take an edge and then, okay, yeah, 4. Yeah, okay. All right. One conjecture down. The new conjecture is 14 over 3.
I think that's a bit bold based on one example.
Oh, I totally believe it. 14 over 3. It sounds perfect to me.
Yeah, okay.
Thanks, James. Damn. All right, it's going to be small, but it's apparently not 4. It's 14 over 3. Okay, so let's move on to average plane size now. So there's just a statement of the results. I'm going to give a sketch of a proof of that, a very quick one. So it turns out that the notion of, so you basically want to, at least for the more, I could state this part of the result without going into the definition of 2 degenerate and 3 degenerate sets, but for higher ranks, it's a probably good place to do it. So I'm going to call a set 2 degenerate if it's got rank at most 2. You should think of a line, because usually they will be lines. And for 3 degenerate sets, you should think of either planes or a pair of skew lines. So it's going to use a set of rank at most 3, or it's going to be a pair of skew lines. So that's what I mean by a 2 degenerate and 3 degenerate set. And you can restate our main theorem by crossing out rank 4 and just saying that the average plane size is bounded by a constant unless M is 3 degenerate, right? So unless your matroid is either a set of points in a plane or it's a pair of skew lines, your average plane size is bounded. And what happened in Beck's theorem is you took the longest line. What we're going to do, so you took the largest 2 degenerate set. So what we're going to do is something slightly more intricate. We're going to take the largest 3 degenerate set. So that's either a plane or a pair of skew lines. And inside that set, we're going to find the largest 2 degenerate set, which is a line, essentially. Right, so I take the largest 3 degenerate set in my matroid, and within that, I take the largest 2 degenerate set. And what we proved was, if you do that, and the matroid, if the matroid's not 3 degenerate, then you get a good estimate on the number of planes, an estimate that's correct up to a constant factor. And that estimate is n times n minus the size of the 2 degenerate set times n minus the size of the 3 degenerate set. So you got some number, and that is the number of planes up to some multiplicative error term. Now, this result is all is essentially proved in a paper of Lund's, except he has another condition I'll talk about later. So he didn't quite prove this. He only proved it for matroids that are far enough from being 3 degenerate. We prove it for matroids that are not 3 degenerate. Okay, so we have this bound on the, we have this good estimate on the number of planes. And I will point out that I'm not going to go into the proof of this result at all. It's not that complicated, but it's a bit technical. But in a lot of ways, it's the most interesting, mathematically interesting part of the paper. I mean, you're really getting at structure when you're like if you're interested in plane size, this 3 degeneracy is really the right notion. And so there's a lot. It's not. There are nice techniques that come up in this part of the paper. Okay. So now when I want to compute averages, we're going to do the analogous thing to which we did in the lines. So we look at this number n times n minus d2 times n minus d3. So what does that make you think of? Well, it makes you think of taking ordered triples, where E is chosen arbitrarily from your matroid, F is taken outside the 2 degenerate set, and G is taken outside the 3 degenerate set. And I want them to be independent. So I want those 3 points to span a plane. Right, in the case of lines, we did the same kind of thing, and we asked that E was not equal to F, so it spanned a line. Here we got 3 points to span a plane. And the set of these, the number of these triples is within a constant factor of the number of planes. So now what we need to do is to relate this set to the sum of the plane sizes. If I can relate the sum of the plane sizes to this set in a nice way, then I'm done. Now, in the case of lines, there was only well, we basically saw that the long line itself played a special role. Here there'll be more planes that play a special role. So that planes that contain the set D2, the special line, they're not going to be helpful because I've got to choose 2 points outside that line, F and G. And so I won't count planes that contain the line. I'm also not going to count planes that are contained in D3 because I need to choose the element G outside D3. So for the planes that are contained in D3 and for the planes that contain D2, it's hard to relate them to these triples. But for the other planes, I can try to use, I can think about the sum of the plane sizes. So for the planes that are spanned by the triples, I can hopefully use some aggregation to relate the sum of the plane sizes to the size of that set script T. For the special planes, there aren't too many of them. It's easy to prove that there's only linearly many of them. So for example, if you contain some fixed line, then there's clearly only linearly many of those because you only get to choose 1 point off the plane, off that line to span the plane. And if you're contained in the degenerate set, if the 3 degenerate sets are plane, there's only one special thing in that case. And if it's a pair of skew lines, there's again only linearly many planes that are contained within the union of 2 skew lines. So there's not very many of them. And because of the fact that there are not very many of them, it's easy to show that the sum of the sizes of these planes is going to be fairly small in comparison to the number of planes, which is like we know what the number of planes is roughly. So I'm skipping some details here, but they're not very interesting details and they're easy details. So for these exceptional planes, they're not very difficult to show that they're not going to significantly add to the average. And then you have to look at the planes that are spanned by triples in script T, and you need to show that each one of those planes is determines a significant number of distinct triples in script T. And this is just using basis exchange. I won't go into the details, but you can use basis exchange just to sort of get the right number of bases that you can order in a way that works. So every plane is actually determining a lot of distinct triples in script T. And of course, every triple in script T determines a unique plane. And so now when I sum up over these planes that are determined by triples in script T, if I sum up the size of P minus 2, I'm getting at most script T and the size of script T, and that is in the order of the number of planes. And that tells you that the average size of these planes is bounded. And we already knew that the average size of the other planes didn't contribute much to the average either. Even just a point of observation here. These planes are actually not bounded, don't have bounded average size, but we're comparing them to the number of planes, not to their size. So these are big planes, but there's very few of them. And you prove that they can't contribute much to the entire average. And again, here, most of the planes are determined by these triples. And so here you really get that the average of those planes is bounded. Average size of those planes is bounded. But when you combine those two facts together, you get that the average plane size is bounded overall. And that's a very brief sketch of the way our theorem works. Do anyone have any questions about that before I move on? Okay, so what I want to talk about in the rest of the talk is various extensions of this, things you can get from it, and ways you can generalize it. So first of all, I mentioned earlier that although our results stated for rank 4 matroids, it applies to matroids of rank at least 4. But this exceptional case, being the direct sum of two lines, is no longer important in higher rank, because in rank 5, you can't be the direct sum of two lines. If I take the direct sum of two lines, I get a rank 4 matroid. So that says that if you have a simple real representable matroid with rank at least 5, the average plane size is just bounded. But you don't need any conditions at all once you're in rank at least 5. So we were able to generalize that to higher rank flats. So if you take a simple real representable matroid with rank at least 2 times k minus 1, then the average size of a rank k flat is going to be bounded above by some constant depending only on k. So if I specialize this to the case that k is 3, so I'm talking about planes, I get a bound of 5, which is exactly the corollary above. Right, so this is just a general result that holds for rank k flats. Now, one slight problem is, well, we'll see in a moment, that we don't get this result as an extension of understanding really what happens. So for example, for for rank 4 flats, we don't really know what's going on in rank 5. We really have to go up to higher rank before we can say anything. So it's a bit different from what we see in planes. So let me talk a little bit about what goes into this proof. So what we need for this proof is a generalization of the notion of degeneracy. I talked about 2 degenerate sets and 3 degenerate sets. And now I'm going to define a k-degenerate set. So a set's k-degenerate if you can partition it into sets each of rank at least 2, so that when I sum up the rank of each of those sets minus 1, I get less than k. That's a bit of a weird thing, but the construction guarantees that if you take a rank k flat, it has to contain one of the sets x1 up to xt. So let me explain why that's the case. So suppose I give you a flat that doesn't contain x1 up to x in any of the sets x1, x2 up to xt. I give you a flat that does not contain one of those things. And now take a basis of that flat. How many elements can it contain from x1? Well, I can't span x1, so it can contain at most the rank of x1 minus 1 elements from x1. And etc. Right? So the rank of the flat is going to be at most the left-hand side here. I took a basis and it contained at most that many elements from x1 and that many elements from xt. So it's the basis contains at most that many things. So if I take a flat that doesn't contain any of x1 up to xt, then its rank is at most the left-hand side there. So if I take so if I've got this strict inequality now, and I take a rank k flat, it has to span one of x1 up to xt. That's what I get from this degeneracy. And now let's think about why that's related to average flat sizes. So suppose you give me an example which has this k degeneracy. Add a point freely to x1. It still contains the same degeneracy problem. And I can now add 1,000,000 points to each of x1 up to xt freely. Like each set, I just add 1,000,000 points freely. And now the average size of a rank k flat is going to be at least 1,000,000, because I just added 1,000,000 points to each of those sets. And every rank k flat has to contain one of those sets. So once I get an example that's k degenerate, I can make other examples where the average flat size is arbitrarily large and it's still k degenerate. So k degeneracy is a real problem when it comes to flat sizes. But if you've got k degeneracy, it really says this is not a good example from a point of view of computing average flat sizes. A very natural thing to conjecture is that k degeneracy is exactly the problem, because that's what we saw in rank 2 and 3. So for lines and planes, we saw that notion of degeneracy really being the issue. But this isn't the case. So the natural thing to believe is that if I take a rank k, if I take a matroid, the average size of a rank k flat is going to be bounded above by some constant depending only on k, unless the matroid's k degenerate. So as I said, that's false, and you can get a counterexample by starting out with the cycle matroid of k4 and then gluing long lines onto the 3 points of a triangle, as depicted here. So so I take this triangle in the cycle matroid of k4 and I just two-sum a very long line off each of those points. This is going to give you a rank 6 matroid. And if you look at the rank the rank 5 flats, every rank 5 flat is going to contain one of these lines. And so if these lines are really, really big, the average size of a rank k flat is going to be huge. But this matroid, you can prove, isn't 5 degenerate. So there are other problems, and we don't understand what's going on here. So there are definitely issues, but we don't understand those issues. Nevertheless, we're still going to do the same kind of thing we did for planes. So I'll take the size, so for some fixed k, I'll take the largest k degenerate set in my matroid. Within that, I'll take the largest k-1 degenerate set, etc. And we call that this structure a stratification of the matroid. And what Lund proved is that as long as the number of, well, as long as your matroid is far away from being k-degenerate, and by being far from k-degenerate, I'm saying that there's a lot. So if I take the largest k-degenerate set, there's a lot of elements outside that k-degenerate set. There's at least some fixed constant. So some fixed constant depending only on k. So if your matroid is far enough from being k-degenerate, then the number of rank k flats is what you would by now expect to be the number. Right, I mean, that's the same kind of form as we've seen in the lines and planes case. So that was the result that Lund proved. So for planes, that's not quite, I mean, so for planes, our result has a C3 equal to 1. And his result's got some arbitrary constant. What we proved as a corollary to his result is that we can replace this condition here on being too close to your matroid being too close to being degenerate. We could replace it by the rank being at least twice k-1. And roughly the reason this is true is that degenerate sets can't have very high rank. So I won't explain that any further, but the rank of a k degenerate set is less than 2k. And you end up getting, so so as long as the rank is at least 2k, we have a very good estimate, an estimate that's correct up to a multiplicative factor on the number of rank k flats. We also have a theorem that tells us that as long as our matroid isn't k degenerate, we also get a matching result on the sum of the flat sizes, the rank k flat sizes. And this second result, this theorem here is basically an analog of what I was explaining for lines and planes. This you take these tuples and you do this aggregation. So you end up with the same thing that happened for lines and planes. You get these special planes that don't come from the tuples and the ones that do come from the tuples. For the rank k flats that come from the tuples, the argument's essentially the same. It's just a bit more complicated in the case that you have the rank k flats that don't come from the tuples. Even though they're not very numerous, they take most of the work to show that they don't destroy the average. Okay, and when you combine those results together, you get exactly what I said earlier, that if you combine these results, then as long as your rank is at least 2 times k-1, as long as your rank is at least 2k-1, then the average size of a rank k flat is bounded by a constant, because you've got this lower bound on the number of rank k flats matching the upper bound on the sum of the flat sizes up to a multiplicative constant. Okay. So far I've talked about average line size, average plane size, average size of rank k flats. And now I'm going to just talk about the average size of a flat where I don't fix the rank. So I'm going to look at all of the flats in the matroid. And take an average there. Of course, if I'm thinking about a rank 4 matroid, If the matroid isn't just the union of two lines, then from our result that the plane size, the average plane size is bounded, and from Melchior's result, the average line size is bounded, and you could put that together to get that the actual average flat size is bounded in the matroid. The only big flat is the single large one, but you can just aggregate that together with the points. So that's what happens as long as your matroid's not the union of two lines. But what happens if your matroid is the union of two lines? Well, if your matroid's the union of two lines, then you've only got a linear number of planes, but you've got a quadratic number of lines. So there's a lot more lines, and they're all 2-point lines. Well, except for those two long ones. You know, a lot of 2-point lines, and they cancel out the effects of the few big planes. So what you end up with is that the average flat size is bounded without any conditions. So for every simple rank 4 real representable matroid, the average flat size is just bounded. We conjecture, and in fact think we can prove, that the average flat size in a simple rank R real representable matroid is also bounded by some constant that depends only on R. We haven't written the proof down yet, so I'm not going to call it a theorem. I'll call it a theorem question mark, but I think that's true. I'm not even, I don't even know if I'll say the stronger conjecture now. James is in the audience because he's going to just tell me what about some 3-element matroid that's obviously a counterexample. But I think the bound is really good. I've written a ridiculously strong bound here, but I think it's going to be a small number like R plus a constant. That constant might even be 0 as far as I know. I don't know any counterexample to that. Actually, I might know a counterexample, but I don't know. I definitely don't know a counterexample to R plus 1 off the top of my head. But I think it's going to be R plus a constant. Okay. So what about complex representability? Well, there is an analog of Melchior's result for complex representable matroids. And that's due to Hirzebruch. So Hirzebruch showed that a simple rank 3 complex representable matroid has average line length less than 4. I doubt that Hirzebruch knew what a matroid was, but his result says that. And all of our results are, in fact, a complex representable, not real representable. So all of our main results, all of our techniques are purely matroidal. And we use theorems that are out of the box for real representable, like Beck's theorem. And there are analogues of these theorems known for complex representable. So we could have just as well started with those, and you get the theorem for complex representable. So it's no more difficult going from real to complex for us. But the theorems proving those earlier results for complex representable is typically much harder than proving it for real representable. When I last spoke about this material, Peter asked me if this 4 in Hirzebruch's result is best possible. And I spent a bit of time thinking about that. So the matroid there shows you can't write less than 3 because that's the ternary affine plane, and all the lines have length exactly 3. But that's still a fair way from 4. It's a fairly intimidating question because Hirzebruch's theorem, this theorem of Hirzebruch was proved using machinery and algebraic geometry, and that machinery doesn't look like it can give you anything better than 4. I don't think, from what I've seen, I don't understand it very well, but from what I've seen, it doesn't seem to be able to show you that you can't have matroids, complex representable matroids, where all the lines have length exactly 3 or 4, but the average is close to 4. The things that I've looked at don't seem to be able to say anything about such examples. So just briefly, why is the ternary affine plane complex representable? Over GF3, if you take 3 parallel lines in this affine plane, they actually meet at a point at infinity. Whereas if you represent it over the complex numbers, you get this Dowling geometry. Those 3 lines are not copunctual. And for Dowling geometries, the representability is only dependent on the multiplicative group. And the complex numbers contain all cyclic groups as subgroups. So you can get other examples where the average goes strictly above 3. And with these Dowling geometries, the best you can get is 3 3/13. But there is another example due to Gervais and Pecora, which is a 21 element matroid where all the lines have length 3 and 4, and the average line length is 3 3/7. And that currently is the best thing that I know. That picture there is not actually a representation of the matroid. That just shows you the 4-point lines in the matroid. The 3-point lines aren't depicted. It's obviously not going to be a straight line construction because that's real representable, right? It's got average line length. This thing's got average line length bigger than 3. So being a sucker for a conjecture, I'll conjecture that that example is as bad as it gets. So I think the average line length in a rank 3 complex representable matroid on n elements is at most 3 3/7. And moreover, I'll conjecture that the average actually goes, the average goes down to 3 as the number of points goes off to infinity. So with the Dowling geometries, you're only getting a few long lines and you're getting quadratically many 2-point lines, 3-point lines. And so as these things get bigger and bigger and bigger, your average tends down to 3. Okay, so let me just finish off with 2 purely matroidal open problems. So we can't hope to get purely matroidal theorems like Melchior's because if you look at a projective plane of order P, the lines have length P plus 1, so the average, and if you take P increasing, the average line length is unbounded, right? I can make matroids where the average line length is as big as I like, easily. But this is really just like an instance of a bunch of conjectures, but let me just state it in a simple case. So I conjecture that if you take a simple rank 5 matroid and you bound the average line length, then it also bounds the average plane size. So here I'm saying if the average line length is at most 3, then the average plane size is at most 1 million. If this conjecture is true, it'll be extremely strong because it's basically saying that as soon as you know that Melchior's result is true for real representable matroids, you automatically know that in rank 5, the average plane size is bounded. We had to work fairly hard to prove that result, and this would just give it for free. I can't go down to rank 4 because there are matroids where all the lines have length 2 in rank 4 and all of the planes have exactly whatever number you want, 17, a million, whatever, using design theory. So you have to go up to rank 5 for this to be true, but I conjecture that it's true in rank 5. But I think if this was provable, it would be a very, very deep theorem. It would explain a lot of difficult things. And when I showed this conjecture to Rutger, he asked a really natural question. What about the converse? If I bound average plane size, do I also bound average line length? And it looks like it's just got to be true. So if I take a simple rank 4 matroid, or matroid rank at least 4, and I tell you that all the planes have size at most 10, surely all the lines have most 1 million. So if the average line length is at most, or if the average plane size is at most 10, surely the average line size has to be at most 1 million. It just looks like it has to be true. But I can't prove it. And so there was a previous conjecture that was called the shameful conjecture in matroid theory, but it's been proved now. So I'm proposing this is the new shameful conjecture. Since it's got to be true, I'm sure it's when somebody figures out why it's true, the proof is going to be short, and I just don't know how to do it. And I've told it to a few other people and nobody else has jumped in with a proof yet, but I'm pretty sure this has got a nice short proof. I just don't know how to prove it. Anyway, I will leave you with that. Thanks for your attention.
Okay, thank you, Jim. So on the count of 3, let's all unmute and give Jim a round of applause. 1, 2, 3. Does anyone have any questions?
I have a question about why does it always odd numbers for your rank? Why is it always 2k minus 1? Where's the odd?
I think there's the underlying reason why it's true is that there's something called the top, well, it's not used in the result, but there is something called the top heavy conjecture, which is now a theorem. It's actually a theorem for all matroids that tells you that the number of rank K flats increases up to half the rank. And for that, you need this -1. And so basically, that basically tells you that when you take a matroid of that rank and then I truncate it down to rank K plus 1, then the hyperplanes are going to be the most numerous things. And so it basically avoids any problems. And the degeneracy, when Lund introduced it, he was basically trying to prove that top heaviness. He was trying to find a structural parameter to relate to top heaviness. So instead of saying that up to halfway, the number of flats is increasing, he wants to know when is the flat size increasing to. So what's the structural problem that stops the flat size from increasing? You kind of expect the number of flats to increase. If I look at the number of points and lines, you sort of expect it to be going up, typically in a real representable matroid. And basically he introduced this notion of degeneracy as a hopeful explanation as to why that stops happening. And that number just happens to come up in his proof. So if you truncate a matroid of rank 2k minus 1 down to rank k plus 1, then its flat sizes will be increasing up to the size of the hyperplane. The number of flats will be increasing up to the size of the hyperplane. I don't know if that's an explanation or not, but that's the way see these results.
Yeah, thanks.
Any other questions? Well, maybe I can ask one. So is there any hope for going beyond complex representable, like maybe finding some finite set of matroids that if you forbid as minors, you get bounded average plane size or something like that?
What I would like to see before that, I mean, I think that there are things that might go in that direction, but I think so. The thing I would like to understand first is what happens if you look at average line size, say, in a matroid representable over a field of characteristic P, but maybe an infinite field of characteristic P. And I think the obstruction is going to be an affine geometry over the base field. So if I fix some fixed rank and I exclude affine geometries of that rank over the base field, then I think the average line size will be bounded above by a constant. And I think something like that's probably true in more generality, so that you would end up basically having affine geometry restrictions causing the problem, but I think it would be exceptionally difficult to prove.
Hmm.
I think there's maybe some hope for what I was saying for like infinite fields with finite characteristic, but even that I think is going to be very hard. And once you get it for average line length, I kind of imagine you wouldn't, it should push through to other flat sizes. But yes, I think that there's a lot of scope for generalizing this stuff in matroid theory, but I think that it's all going to get extremely hard.
Yeah. Okay. Any other questions?
Yeah, how did you come across the stuff of Lund?
Oh, that's actually, I think Matthew Croker can take a lot of credit for that. I believe he found those papers. However, Ben Lund works in the same department as Rutger. So Rutger had already spoken with Ben Lund about geometric type questions before.
So he's a projective geometer, is he?
Yeah.
Yeah. Okay.
Okay, so maybe I'll stop the recording and we can continue the discussion off the air.